Today, we're going to delve into an important topic in the field of nuclear energy: radioactive waste disposal. Radioactive waste is a byproduct of nuclear power generation, and it requires proper handling and disposal to ensure the safety of both people and the environment. In this episode, we will discuss what you need to know about radioactive waste disposal. So, let's get started.
Before me dropping value bombs of this video, I would like to introduce the Nuclear Power Engineering Principles course, now available on Udemy. This comprehensive course is your ticket to mastering the principles of nuclear power engineering and taking your career to new heights. Packed with engaging lectures, this course is designed to provide you with a deep understanding of nuclear power engineering principles. And the best part, upon completing the course, you will receive a prestigious certificate of completion to showcase your newly acquired skills and knowledge. It is a valuable credential that can open doors to exciting career opportunities in the nuclear power industry. Don't miss out on this incredible opportunity to unlock your potential with Nuclear Power Engineering Principles course. Enroll now and gain access to this top-rated course at an unbeatable price. But hurry, as this offer won't last long. Join us today and take the first step towards a successful career in nuclear power engineering. Enroll now in the Nuclear Power Engineering Principles course on Udemy and unlock your potential. Don't wait and start your learning journey now. Now, if you're interested, the link to this course is provided in the video description below.
First, let's start with understanding what radioactive waste is. Radioactive waste refers to materials that contain radioactive isotopes, which are atoms with unstable nuclei that undergo radioactive decay, emitting ionizing radiation. Radioactive waste can come from various sources, including nuclear power plants, medical facilities, research institutions, and industrial processes that use radioactive materials. It can take different forms, such as liquids, solids, or gases, and may vary in terms of radioactivity levels, ranging from low level to high level, depending on the type of isotopes and their half-lives, which determine how long it takes for them to decay. Radioactive waste is hazardous due to the potential harmful effects of ionizing radiation. Ionizing radiation can penetrate living tissues and cells, damaging DNA and potentially leading to health risks, such as radiation sickness, cancer, and genetic mutations. Therefore, proper management and disposal of radioactive waste are crucial to protect human health and the environment. Radioactive waste is classified into different categories based on its radioactivity levels and the type of isotopes it contains. The classification may vary depending on local regulations and standards, but generally, radioactive waste is categorized as low-level, intermediate-level, or high-level waste. Let us go over these types. Low-level waste, LLW, typically includes materials with low levels of radioactivity, such as contaminated tools, protective clothing, and equipment used in nuclear power plants, research laboratories, and medical facilities. LLW can also include naturally occurring radioactive materials, NORM, such as residues from mining and mineral processing. LLW usually contains short-lived isotopes and has relatively low radioactivity levels, requiring minimal treatment before disposal. Intermediate-level waste, ILW, includes materials with higher levels of radioactivity, such as used fuel rods from nuclear reactors, some medical and research waste, and contaminated components from decommissioning nuclear facilities. ILW may contain both short-lived and long-lived isotopes and requires more stringent containment and isolation measures due to its higher radioactivity levels and longer half-lives. High-level waste, HLW, is the most radioactive and hazardous form of radioactive waste, primarily consisting of used nuclear fuel rods from nuclear reactors. HLW is generated during the process of extracting energy from nuclear fuel and contains long-lived isotopes that can remain radioactive for thousands of years. HLW requires the highest level of containment and isolation due to its high radioactivity levels and long half-lives. Transuranic waste, TRU, refers to waste that contains artificially created radioactive elements, also known as transuranic elements, which have atomic numbers higher than uranium, 92. True waste is typically generated from nuclear weapons production, research and development, and other nuclear activities. True waste may include contaminated equipment, tools, and materials, and requires special handling and containment measures due to the potential long half-lives of some transuranic elements. Lastly, spent nuclear fuel refers to used fuel rods from nuclear reactors that have been removed from the reactor core and are no longer capable of sustaining a chain reaction to generate electricity. Spent nuclear fuel contains a mixture of radioactive isotopes, including both short-lived and long-lived isotopes, and requires special handling and containment measures due to its high radioactivity levels and potential for reactivity. In addition to the above types, there may be other forms of radioactive waste generated from various nuclear-related activities, such as contaminated soil, water, and air, as well as radioactive sealed sources, and radioactive waste from research and medical facilities. Understanding the different types of radioactive waste is crucial in developing appropriate management and disposal strategies. Low-level waste, intermediate-level waste, high-level waste, transuranic waste, spent nuclear fuel, and other radioactive waste all have unique characteristics that require specific handling, containment, and isolation measures to ensure safety and protection of human health and the environment. Now, let's discuss the different methods for radioactive waste disposal. The three common methods are temporary storage, permanent disposal in deep geological repositories, and nuclear fuel reprocessing. Temporary storage involves storing radioactive waste in facilities designed to contain the waste safely until it decays to a lower level of radioactivity. Deep geological repositories are engineered facilities designed to store radioactive waste in layers of rock deep underground, ensuring long-term containment. Nuclear fuel reprocessing is a process that extracts valuable materials from used fuel rods for reuse, reducing the volume of radioactive waste. Now, let's take a closer look at the different methods for radioactive waste disposal. The first is temporary storage. Temporary storage involves storing radioactive waste in facilities designed to contain the waste safely until it decays to a lower level of radioactivity. This method is often used for low-level radioactive waste, which includes items such as protective clothing, tools, and contaminated materials. Temporary storage facilities are typically located at the site where the waste is generated, such as nuclear power plants, medical facilities, or research institutions. The waste is packaged in specially designed containers that are designed to prevent leaks or releases and monitored regularly for any signs of degradation or contamination. The second type is deep geological repositories. Deep geological repositories are engineered facilities designed to store radioactive waste in layers of rock deep underground, ensuring long-term containment. This method is used for intermediate-level and high-level radioactive waste, which includes used fuel rods from nuclear reactors and other highly radioactive materials. The waste is packaged in robust containers and transported to the repository site, which is carefully selected based on factors such as geology, hydrology, and population density. The waste is then placed in layers of rock formations, such as clay, salt, or granite, that are geologically stable and expected to remain intact for thousands of years. Multiple barriers, including engineered barriers such as containers and natural barriers like geology, are used to prevent the release of radioactive materials into the environment. The third type is nuclear fuel reprocessing. Nuclear fuel reprocessing is a process that involves extracting valuable materials from used fuel rods for reuse and reducing the volume of radioactive waste. This method is considered more controversial and is currently not widely used due to concerns related to nuclear proliferation and potential for misuse of extracted materials. However, it has been employed in some countries as a method to manage radioactive waste. The process involves separating the valuable materials from the used fuel rods, such as plutonium and uranium, for reuse in the production of new nuclear fuel. The remaining waste, known as nuclear waste, is typically stored and eventually disposed of using other methods, such as deep geological repositories. And lastly, we have advanced technologies. There are ongoing efforts to develop advanced technologies for radioactive waste disposal. These technologies aim to improve the safety and efficiency of disposal methods. For example, research is being conducted on advanced waste treatment processes, such as advanced thermal and chemical treatment methods, which could reduce the volume and radioactivity of radioactive waste. Additionally, there are studies on the development of advanced packaging and containment materials that could enhance the long-term stability and integrity of waste containers. Furthermore, innovative approaches to site selection, such as using advanced geological and hydrological characterization techniques, are being explored to ensure the optimal location for deep geological repositories. Radioactive waste disposal is heavily regulated to ensure safety. Governments and international organizations have established strict regulations and guidelines for the handling, transportation, and disposal of radioactive waste. Safety measures include packaging waste in specially designed containers, transportation in secure vehicles, and monitoring for leaks or releases. Additionally, disposal sites are selected carefully, taking into account factors such as geology, hydrology, and population density to minimize the risk of exposure to radioactive materials. The International Atomic Energy Agency, IAEA, is the global authority responsible for promoting the safe and secure use of nuclear technology, including the management and disposal of radioactive waste. The IAEA establishes safety standards, guidelines, and recommendations that member states are encouraged to follow in managing radioactive waste. These standards cover various aspects, including waste characterization, handling, transportation, storage, and disposal. Many countries have their own regulations and guidelines governing the management and disposal of radioactive waste. These regulations may be developed by national nuclear regulatory authorities or other relevant government agencies to ensure that radioactive waste is handled and disposed of safely and in compliance with national laws and regulations. One critical aspect of managing radioactive waste is proper waste characterization, which involves determining the characteristics and properties of the waste, including its radioactivity levels, physical form, and chemical composition. Waste characterization is crucial in identifying appropriate handling, storage, and disposal methods, as well as assessing potential hazards and risks associated with the waste. Radioactive waste must be packaged and transported in accordance with strict regulations and safety measures to prevent releases of radioactivity and protect workers, the public, and the environment. This includes using specially designed containers, shielding, and labeling to ensure safe handling and transportation of radioactive waste. Storage and disposal facilities for radioactive waste must meet rigorous safety requirements, including containment measures to prevent the release of radioactivity into the environment. These facilities may include engineered barriers such as waste containers, geological repositories, and other containment structures to isolate the waste from the biosphere and prevent potential contamination of air, water, and soil. Radioactive waste management facilities typically employ monitoring and surveillance measures to ensure the safe and secure handling, storage, and disposal of radioactive waste. This may include radiation monitoring, environmental monitoring, and surveillance of waste packages and disposal sites to detect and address any potential issues or breaches of safety measures. In managing radioactive waste, it is essential to engage and involve stakeholders, including local communities, indigenous populations, and other relevant parties, in the decision-making process. This includes providing information, transparency, and opportunities for public participation to ensure that concerns and perspectives are taken into account in the development and implementation of radioactive waste management plans. Lastly, education and training of workers involved in the handling, transportation, storage, and disposal of radioactive waste are critical in ensuring safe and secure practices. Proper training on radiation safety, waste management protocols, and emergency response procedures is essential to prevent accidents, mitigate risks, and ensure compliance with regulations and safety measures. Community engagement is a critical aspect of radioactive waste management, as it involves actively involving local communities, indigenous populations, and other stakeholders in the decision-making process. Engaging communities in the planning, development, and implementation of radioactive waste management plans helps ensure that their concerns, perspectives, and needs are taken into account, and fosters trust, transparency, and cooperation between stakeholders. Public perception and attitudes towards radioactive waste management can vary widely and may be influenced by various factors, including cultural, social, economic, and historical considerations. Some members of the public may have concerns or fears about the safety, environmental impact, and long-term risks associated with radioactive waste, while others may view it as a necessary and acceptable form of energy production. Understanding the public's perception and attitudes towards radioactive waste is crucial in developing effective communication and engagement strategies. Effective communication and information dissemination are essential in community engagement efforts related to radioactive waste management. Providing accurate, transparent, and understandable information about the risks, benefits, and safety measures associated with radioactive waste can help address concerns, clarify misconceptions, and foster informed decision-making. Communication channels may include public meetings, stakeholder forums, educational materials, social media, and other means to reach out to the community and facilitate two-way communication. Building trust and partnerships with local communities, indigenous populations, and other stakeholders is crucial in fostering positive engagement in radioactive waste management. This involves establishing meaningful relationships, listening to concerns, addressing questions and providing credible information, and involving stakeholders in the decision-making process. Collaborative partnerships can help ensure that diverse perspectives are considered, and solutions are co-developed, leading to more robust and sustainable radioactive waste management plans. Socioeconomic considerations play a significant role in community engagement efforts related to radioactive waste management. These may include the economic benefits and costs associated with radioactive waste disposal facilities, potential impacts on property values, job creation, and other socio-economic factors that may influence local communities' perceptions and attitudes. Understanding and addressing socio-economic considerations are crucial in developing effective community engagement strategies that take into account the unique needs and interests of local communities. Cultural and ethical considerations are also important in community engagement efforts related to radioactive waste management. Indigenous populations and local communities may have unique cultural, ethical, and spiritual perspectives on land use, natural resources, and the environment. Respecting and incorporating these perspectives in radioactive waste management plans can foster trust, mutual understanding, and sustainable solutions. And lastly, education and outreach efforts are critical in community engagement related to radioactive waste management. Providing educational materials, workshops, and training sessions on radioactive waste, radiation safety, and waste management protocols can help increase awareness, understanding, and knowledge among community members. This can empower them to participate effectively in decision-making processes and contribute to informed decision-making. As technology advances, there are ongoing efforts to develop new methods and technologies for radioactive waste disposal. This includes research on advanced waste treatment processes, improved packaging and containment materials, and innovative approaches to site selection and community engagement. These developments aim to enhance the safety and efficiency of radioactive waste disposal, while minimizing potential risks to human health and the environment. Advances in waste treatment technologies, such as advanced separation, encapsulation, and immobilization techniques, may offer more efficient and effective ways to treat and manage radioactive waste. These technologies may include advanced reprocessing methods, such as partitioning and transmutation, which can reduce the volume and radioactivity of waste, or advanced vitrification techniques that can immobilize waste in a durable glass matrix for long-term storage. In addition to traditional disposal methods, such as geological repositories, future developments may include alternative disposal methods, such as deep borehole disposal, where waste is placed in deep boreholes drilled into rock formations, or subsea bed disposal, where waste is stored in stable sediments deep below the ocean floor. These alternative methods may offer unique advantages in terms of safety, security, and environmental impact and may be explored as potential options for radioactive waste management in the future. Advances in monitoring and surveillance technologies, such as remote sensing, robotics, and sensor networks, may offer improved capabilities for monitoring and managing radioactive waste repositories. These technologies can provide real-time data on various parameters, such as temperature, pressure, and radiation levels, to ensure safe and secure storage and containment of radioactive waste. They can also facilitate early detection of potential issues or anomalies, allowing for prompt response and mitigation measures. Future developments may involve the implementation of integrated waste management systems that combine various waste treatment technologies, disposal methods, and monitoring approaches to optimize the overall management of radioactive waste. These systems may be designed to minimize waste generation, maximize waste treatment efficiency, and ensure long-term safety and security. Integrated waste management systems may also incorporate principles of circular economy, where waste is viewed as a resource that can be recycled, reused, or repurposed to minimize environmental impact. Advances in nuclear energy generation technologies, such as advanced reactor designs, small modular reactors, SMRs, and Generation 4 reactors, may impact the management of radioactive waste. These technologies may offer improved safety features, higher fuel utilization, and reduced waste generation, which can positively influence the overall radioactive waste management process. Future developments in radioactive waste management may also involve increased emphasis on public engagement and stakeholder involvement. This may include innovative approaches, such as participatory decision-making, citizen science, and co-design of waste management plans, to ensure that diverse perspectives are considered, and decisions are made collectively. Emerging technologies, such as virtual reality, social media, and online platforms, may also be utilized to facilitate broader public engagement and participation in radioactive waste management discussions. Future developments in radioactive waste management may also involve updates to policy and regulatory frameworks at the national and international levels. These may include revisions to waste classification, disposal criteria, and safety regulations based on scientific and technological advancements, societal changes, and evolving public perceptions. Updated policy and regulatory frameworks may provide a more robust and adaptive approach to radioactive waste management, addressing emerging challenges and opportunities. Future developments and technologies hold promise in advancing the field of radioactive waste management. From advanced waste treatment technologies to alternative disposal methods, innovative monitoring and surveillance technologies to integrated waste management systems, advances in nuclear energy generation, public engagement, and policy frameworks, the future of radioactive waste management is dynamic and evolving. In conclusion, radioactive waste disposal is a critical aspect of nuclear energy production. It requires careful handling, transportation, and containment to ensure the safety of people and the environment. Strict regulations, safety measures, community engagement, and public perception are essential components of the radioactive waste disposal process. As technology continues to advance, we can expect further developments in this field. We hope this episode has provided you with a better understanding of what you need to know about radioactive waste disposal. If you're enjoying learning about the exciting world of engineering on our channel, be sure to hit that like button and subscribe to our channel. It really helps us out, and you won't want to miss any of our upcoming videos.